Good morning, good afternoon, good evening, whenever you're watching this video. Back for Related Rates Day 2, Part 3 of my lesson. Part 1, we looked at the strategy, the 6 steps. In Part 2 of the lesson, we did one example, which was relatively easy, not terribly difficult. And here we're going to look at some more from the packet. So you probably went home and looked over the packet, kind of got an idea of the different problems that we're going to do. And now we're going to work them all out. Maybe you tried some of them. Maybe you got some of the homework done as well. All right, here we go. So in the packet, go ahead and take out the packet. And problem number B. In problem number B, I've got a rocket shown is rising vertically. So here's my launching pad, and the rocket is rising vertically at 880 feet per second. When it is 4,000 feet high, how fast is the camera to rocket distance changing at that instant? Here's the camera to rocket distance. The camera is fixed 3,000 feet away from the launching pad. And then I've got some sort of angle of elevation here. We won't need this angle in this problem. In the next problem, we're going to be talking about the angle. So what I want to know is, picture this camera here, and it's focused on the rocket. And in order to focus, it needs to know this distance. And this distance is constantly changing. As the rocket increases its height, this distance here is constantly changing. So step 1, draw a picture. Well, there we go. And name all the variables and the constants. We're going to use t for time. Write down any numerical information. Well, let's see. What do I know? Well, the rocket is rising vertically at 880 feet per second. It's rising at 880 feet per second. Now, what is that really? That's the rate of change of the height of the rocket. And then I want to know what's the rate of change of this distance when it is exactly 4,000 feet high. All right, so all of our variables, t is going to equal time. We need something that relates these together. And as you can imagine, I'm going to have a nice little right triangle here. I'm going to use x, y, and z. And my z is going to be camera to rocket distance. Camera to rocket. Oh dear, my pen's not very good here. Sorry about that. My y is going to be the height of the rocket. Now the x is the distance from the camera to the launching pad, but that's a constant. It's 3,000. X equals 3,000 all the time. What is this? 880 feet per second. It's a rate of change. Be more specific though. What rate of change? The rate of height of the rocket change. Be even more specific. If I'm calling that y, then this is really dy dt, the change in the vertical height of the rocket over time. 880 feet per second. And then finally, what is it we are trying to find? We're trying to find the rate of change of this distance here. Well, using, I call this distance z, so that's what I'm trying to find. dz dt equals, I don't know, that's the thing we're trying to find. All right, now step 4. We want to find an equation that relates all these variables together. And I think it's pretty obvious here with this right triangle. We're going to be using Pythagorean Theorem on this. So Pythagorean Theorem tells me x squared plus y squared equals z squared. Substituting in, I'm going to get, before I substitute in, I'm going to have to do the derivative of this with respect to time, and then substitute in all my numbers. So step 5, differentiate this with respect to time. So I want to find d dt of the x squared plus y squared equals z squared. Implicit differentiation here, and as I do the derivative, I'm going to get 2x dx dt plus 2y dy dt equals 2z dz dt. Now, This x is actually a constant. This is a constant, x squared, 3,000 squared. That's never going to change. There is no rate of change there. So this whole term right here is going to disappear. This whole term, because x is a constant, 3,000. 3,000 squared plus y squared equals z squared. This whole term is going to disappear. It's going to become 0. So what do I have left? I've got 2y dy dt equals 2z dz dt. What am I trying to solve for? I'm trying to get dz dt alone by itself. I'm going to divide both sides by 2z. And I will have, actually I'm trying to get dz by itself, divide both sides by 2z, and I get 2y over 2z dy dt equals dz dt. Now I'm at the point now where I can evaluate. I've got the derivative. I'm going to evaluate the derivative to find the rate of change of the distance from the camera to the rocket. And I'm going to substitute these in. Oh, I notice that I can cancel the 2's there, right? I can cancel the 2's. Substituting in. I want to substitute in my y value. Do I know my y value? I know the dy dt, that's the 880 dz dt. And do I know the y value and the z value? What's the y value and the z value? Well, the original problem said when it is 4,000 feet up. That's my y value. So at 4,000 feet elevation, that's my y value. That's going to go in right here. So I'm going to cancel the 2's. So 4,000 right here. But what is the corresponding z value? Well, when at the instant that the rocket is 4,000 feet high, remember this is a fixed distance. From the camera to the launching pad is the fixed distance of 3,000 feet. So at the instant when the rocket is 4,000 feet high, how far is it at that instant? And of course we can see a little 3, 4, 5 triangle here. This distance would be 5,000. So my z is going to be 5,000. Now if I simplify this, multiply 4,000 times 880 divided by 5,000, I'm going to get 704 is my dz dt. But what is the rate of change? What are the labels here? Well, what does dz dt represent? Rate of change of the distance from the camera to the rocket over time. So the units here are going to be feet per second. All right, and there's our final answer. So 704 feet per second. That's the rate of change in the distance from the camera to the rocket when the rocket is exactly 4,000 feet high. Now, when it's higher, that rate of change is going to be different. Or when it was lower, the rate of change will be different. Because this might be the same, but those numbers will be different. This is Pythagorean Theorem. If this was 3,000 feet here, 3,000 and 3,000, this would be 3,000 root 2. So I would get different 45, 45, 90 triangle. All right, let's take a look at another one. Take out number C, problem C from your packet. All right, a little bit more going on in this one with the angles. Same kind of setup as before. We've still got that rocket. It's rising vertically at 880 feet per second. When it's 4,000 feet up, how fast must the camera elevation angle change at that instant to keep up with the rocket? So picture this. Here's the rocket, 3,000 feet away from the camera, launching into space, and it's getting higher and higher and higher. Here's my y value, my x value, my z value. This angle is going to be changing. It's going to be getting bigger and bigger and bigger. At first, it might be changing very quickly, and then after a while, it's changing maybe more slowly. But what would be the rate of change of that angle when the rocket is exactly 4,000 feet up? What's going to be the units here? The rate of change of what over what? Well, something per second, obviously. But what per second? Well, if we're taking a look at this angle in degrees, my final answer is going to be in degrees per second. How many degrees per second? Or if we do it in radians, it'll be how many radians per second. All right, here we go. So let's crank this thing through, answer all the questions. T is time in seconds. The angle, I'm going to call it theta, is the angle of elevation. Oh, I just noticed I call it phi over here. Well, I'm changing that. I'm going to call it theta now. The x, I don't know whether there's a y here. We'll leave it here. The y represents the height of the rocket. Now, the x value is a constant. X equals 3,000. This 880, what is that? That is my dy dt is 880. And what am I trying to find? What is the rate of change that I'm trying to find? Well, the changing angle here. So I'm trying to find d theta dt. That's my unknown. All right, so now here comes the part where we have to, so we've written down all the information, we've written down what it is we're trying to find. Find an equation that relates all of the variables. What variables? Well, an angle, or changing angle, this side and this side. Let me say it a little differently. An angle, the side opposite from it, and the side adjacent to it. This is not going to be Pythagorean theorem. What equation relates an angle, an opposite, and adjacent? Yes, tangent. Did anyone say that out loud? That would be funny if somebody said that out loud. Tangent. So I know that the tangent of any angle is the opposite side over the adjacent side. So the tangent. Now, as I take a look at this, I want to find the derivative here. Let me fill in some information. The tangent of theta equals y over 3,000. And I want to take the derivative of this. So d dt. So we can see we're going to have to take the derivative of tangent. And we should know this one. Derivative of tangent is secant squared equals, now 1 over 3,000, that's a constant. Just pull that out front. It's not going to disappear because of the y. But what's the derivative of the y value? dy dt. So now take a look at this. Oh, you know what I forgot here? When we've done I forgot the d theta dt here, haven't I? This is secant squared times d theta dt. So in here, very important. Oh, how am I going to squish it in there? I want to put in there d theta dt should be in there. Very, very important. D theta dt. Because the derivative of tangent is secant squared theta d theta dt. And of course, that's what it's all about. That's what I'm trying to find. Equals that. Solving for d theta dt. Oh, it's got a little messy. I'm sorry. Here, let's clean it up. D theta dt is going to equal, now I'm going to divide both sides by secant squared. So I'm going to have 1 over secant squared theta times 3,000 times dy dt. Now, believe it or not, we've got our answer here. The secant squared, I think I could simplify this. 1 over secant squared, we have a formula for that, don't we? The reciprocal formula. What is 1 over secant squared? D theta dt, the rate of change of the angle, is 1 over secant squared. We know that is cosine. So this is going to be cosine squared theta over 3,000 times dy dt. All right, so here we go. So now let's put in the information that we know. All right, so d theta dt is going to be the cosine squared of the angle. Oh, I never found out the angle, did I? I'll work the angle over here in a moment. We need the angle. And then dy dt, that's going to be our 880, and then the 3000. I need to find theta. So let's find theta. At what instant are we trying to find theta? At the instant the rocket is 4,000 feet high. In other words, what is theta, and this is a fixed distance of 3,000, when the rocket is 4,000 feet high? I need to find the theta here. And how am I going to do this? Again, I'm going to use tangent. I know that the tangent of any angle is the opposite side over adjacent. So the tangent of that angle is 4,000 over 3,000. Take the inverse tangent of both sides. The angle is going to be the inverse tangent of, simplify it, 4/3. We're going to need our calculators now. Have you noticed we haven't used calculators a lot in a lot of the derivatives? It's all about knowing the patterns and the different rules. The final evaluation, though, when we go to plug numbers in and actually solve for something like finding a slope or finding an equation, then we need our calculators. That's when it's getting a little bit more difficult. And I need my calculator here. Now, what are we going to do theta in? Radians or degrees? I'm going to go to my mode button. Right now I'm in degree mode, so I'm just going to leave it in degrees. So when I do this calculation, my answer is going to be theta in degrees. So the inverse tangent of 4/3 is 53.13 degrees. So the angle is 53.13 degrees. That's what's going in here. 53.13 degrees over the fixed rate of 3,000 times dy dt. Remember, the dy dt was 880. One more calculation, and as you can see, we're going to need our calculators here. d theta dt in degrees. Now, how do I do the cosine of 53.13 squared? I'm going to use parentheses. Open parentheses. Cosine of my previous answer, 53.13 rounded, close parentheses. So the cosine of that, close parentheses, squared. So now I'm going to do the cosine of that squared, times 880 divided by 3,000 equals, and I get 0.1056. What's the unit associated with this? Degrees per second. So the angle is changing at the rate of 0.1056 degrees per second, so the camera can keep up with that, keep up with the rocket up there. All right, gentlemen, so there's two examples. When we come back tomorrow, or actually later today, if you want to pause the video, jump right to the next video. We're going to do the next two problems, D and E. D is kind of fun and interesting. A ladder, I'm sure you've read it already, a ladder slipping down the building. And problem E is a tough one. We'll talk a lot about problem E, and it's kind of one of the favorite ones for the AP too. All right, so I will talk to you again in a few moments.